So hi everyone, my name is Jingshi Zhang. I'm a fourth-year PhD candidate. So my advisor, Professor Rahman Azari, and another Professor Uta Poshka, she's from architecture department. Professor Derek Hall, he is from electrochemistry department. Julian Wang, he's from architecture engineer. So a little bit of background of the research is the building consumption. This is the data from 2022. Building consumed about 40% of total U.S. energy. And when we look at carbon dioxide emission, building emitted about 35% of carbon dioxide. But in terms of energy source, there's only 12% of renewable energy was used. So it means like we use a lot of fossil fuels still. And we think building schemes are really important because building schemes allows the lighting and the ventilation, fresh air comes in. It keeps good thermal comfort. Some building schemes can work as a structure. It also work as moisture, vapor, and acoustic barrier. Some really advanced building scheme can generate energy or capture carbon dioxide. When we talk about renewable energy and building scheme together, I think BIPV, building into great photovoltaic is the first technology we can think of. So BIPV means we use the photovoltaic panel as for example, as a roof tile. Other examples like a part of opaque wall or some transparent photovoltaic can be used as a window. So there are like more and more photovoltaic are installed recently. It's a very good thing to use a lot of solar panels, but it also causes another problem we call duck effect. So duck effect means from the electric grid point of view, in the middle of the day, the solar panel will produce a lot of electric energy. So the demand is relatively low in the middle of the day. But after 6 p.m. or 7 p.m., the demand goes very high, but there's no solar energy available. So this causes a big problem to the electric grid. This steep ramp need 3 hours to achieve the highest demand and also cause other electrical problems. So the solution for the duck effect is to use electrical energy storage methods. So there are some common electrical energy storage methods, and because we want to find something can be used for buildings, so we will look at a small scale devices, for example, batteries and hydrogen. Both of these two technologies is related to a discipline we call electrochemistry. So electrochemistry is a study the relationship between electrical energy and a chemical change. So it means we use some technology, we can convert fuel to electricity, and also we can convert electricity back to fuel. So we not burn a fuel. This is a chemical reaction in this process. So very common example is the battery. I think if we use a photovoltaic, sometimes we need batteries to store the energy. But for our research, we use a reversible fuel cells. So why we're going to use a reversible fuel cell is there's a study shows a comparison between using batteries and the fuel cell. For long term, over 10 years, the fuel cell will save a lot of money. So like a rechargeable battery, reversible fuel cell can charge and discharge energy. So if it's on the charging mode, it will work as an electrolyzer, so will convert electricity to hydrogen. And when it's discharging mode, it will consume hydrogen and produce electricity. So use one device, we can do this energy store process. So some pictures. So our goal is to create a building cladding panel capable of seamlessly integrating a reversible fuel cell with a photovoltaic, enabling the harvesting, conversion, and storage of solar energy. And why? We integrated electrochemical devices with building skins enable multifunctional cladding panels. Anyway, we need something on the building skin, so why we not make it produce energy or store energy. And the second facility easy installation of energy components. There are some examples to use the fuel cell in buildings, but usually they're located in the mechanical rooms. But right now we wanted to design just a one panel, but we can do the all the like a converter store things. So if we buy this one panel and just put on the building facade, I think it's easy for everyone to use. And the third is suitable for retrofitted building without requiring additional space for energy systems. So yes, so we have the building skin surface, so we can use that. So we don't need a lot of area to install the photovoltaic panels. So the research question first is how can the integration of photovoltaic technologies for energy harvesting be achieved with a reversible PEM fuel cell for energy storage within building skin designs? The second question is like the performance. We would like to know the panel's performance in terms of energy conversion. So here the my research methods. So the first is to conceptualize my panels as part of building skins. And then we developed some prototypes, and we do some experimental testing and also do simulating to see the energy efficiency. So conceptualizing. So this diagram on the right shows like the energy flow within this single panel. So first of all, the solar energy will convert it to electricity. Part of the electricity will directly consumed by the building. And if we have surplus, we will convert this part of electricity as hydrogen. And the hydrogen will be stored in a tank. And then late in the evening or like sometimes if we need electricity, we can convert hydrogen back to electricity again and use it for building. So we proposed to store the hydrogen just within the panel, but it depends on what city, depends on the need we need, depends on like what kind of design. So we also proposed some possible ways to use that panel, like a shading device or a colliding panel, spandrel wall, or second wall. So we make first it's kind of a demonstrator, like so it's not look like a panel, but here we show all the components we need to make the things work. So there's some measurement like show how much hydrogen we can harvest on that day. So this is the first prototype. Okay. Okay. And because the reversible PM fuel cell used in this experiment is not very high efficiency. So we trying to find other high efficient cells for the buildings. So we have a like a new design for that. And so right now I'm working on like the new components we got. Like we're trying to connect them and make them work. So we did some testing, make sure this works. So we can see from like the weather is very important when it's on a cloudy day. We will get a very small amount of hydrogen, but on a sunny day, we can get much more hydrogen. So yes. So this part is like a simulation. We have like a different components in the software, and I did a simulation for two locations, Phoenix and Chicago. We want to see like a different climate. Different climate will have like different impact on the system. So like different location will get a different amount of energy. So here like some comparison between these two locations. And yeah, so yeah, that's like a summary of my research.